is the motor, and it's attached to a kind of disc which will create the, if you can go back to the picture, you can see this disc over here. If I can highlight it, this disc, which is basically what I've drawn in here, and this is in Dutch, therefore I will make it in English. So this is the force of the spring, and as you can see, it's creating a moment or a counter torque which is applied to the motor. And if you don't know what torque is, it's basically represented by the arm times the force, or cross product. I have explained what cross product is in my what is a railgun video, and it's if you don't know what it is, I suggest you watch it. But this spring creates a torque with an arm R, and this torque comes back in the formula above, which then creates the sine wavy, it creates this, which is not good. Therefore we must find a function which will fix that problem for us. So you can see is over here, when the spring is over here, there is no torque, and when it's over here, there's maximum torque. And as if this is a circular motion, of course, we will have the sine wave as explained earlier. So let's take a look at the equations. So what we can see here is a vector representation of the force vector, and what this simply states is that F is equal to a constant times a displacement, and this is in vector representation, and we have discussed vectors in what is a railgun and how does it work, and we have explained it a little bit in there. But as you can see is that we have a torque produced by the spring force, and if we substitute this into there, we get this equation for the torque. And mostly this torque is in the direction of the displacement, and it will vary as you saw in this motion diagram, because at the moment the displacement is in this way, and then it is in this way, and sometimes in this way. So we have in here we have an x displacement, and in here we have a y displacement, and here we also have a y displacement. So we have to write it as a vector function, which this is basically 0, but because we have 3 axes over here and we're working in 3 axes, these two will mostly have a component, and therefore it's a vector, and the r is a vector which is basically always in the same scalar, and it's just rotating. It's not much, but this is basically a constant. Therefore the torque can change, and that's the equation for the torque. That's applied to the motor, which we have to control well, we can't control the torque, but we can control the angular velocity component to be a constant, because if the torque goes up, we just give it more voltage, and therefore the velocity goes up, because the torque is mostly uh, a function of a sine function, and so we can keep the angular velocity constant. And why that is necessary is we will see now. So first of all, we must understand that when this is rotating at or it's already given, if it's rotating at a angular velocity, it will also have a tangent velocity, which we'll call vt, which is also a vector. And that vector we can see over here. We can see that the x component over here, or the x component is over here. We can see it's a function of sine theta, which over here this is 0 and it will go this way. Therefore over here it's maximum, and we have lots of tangent velocities along the way. And for the y component we have a cosine, which is very simple. So what we have here is simply a vector which represents the tangent velocities. And why this is important is because the spring is given by F is k times the displacement, which is also ma. Therefore ma is k times the displacement, and a is k times the displacement times divided by m. And as we can see, it has a. And if we write this as x double dot, this means that this is a derivative of x dot. Therefore it also has a speed, and this speed, which comes out of here, must be equal or less than the velocity the spring has when it's in energized state. Otherwise, what will happen if that's not the case is, if the motor, for example, is a lot faster than the spring, we have a spring in energized state and the motor is around here. Therefore there is this distance that the spring will not deliver a force to the frame, and therefore it will just go instantaneously. It doesn't deliver a force to anything, so nothing happens and you won't leave the ground. And we do not want that. We want to program this angular velocity as a function of the angle it's positioned at, so we can have a optimal designed robot. And for the next equation we use the equation we have derived before, which is simply the voltage, the duty cycle, the current, and the torque. The torque we know, which is this equation. So we know that. We know voltage, we know I, except what we don't know is where where the u is at a certain angle. So if we write this out, we get this equation, which is the angular velocity as a function of the angle. Now we know this one, we don't know this one. We will see later. This is a input variable, so we can make this a constant. This is a constant, this is a constant. This is the variable dependent parts of the equation. This is a constant. Therefore we only have this one, and this one to control, and this one we have to figure out, and we'll see later because it's done with some electronics. So this is a fairly simple equation, maybe not on first sight, but this is this part here. This is simply displacement, and this is the arm. This is R, which is this arm over here. This is just K times U cross the arm, which is torque. You can see over here. K times U times cross the arm. Simple as that. But as you can see, over here we have a cross product and we have a angle. Therefore, there is a value for the angle where this whole term goes to 0. Therefore, we get a certain value C divided by 0. You know what it means? Is that when 90 is approached and minus 90, this whole thing goes to 0, and therefore we will reach a max. And if we go back to this function, we can see that the max are over here, and we have a minus max and a plus max, minus max, as you can see over here. I didn't write it down, but it's there. As you can see, because it has a minus 90 and a plus 90, it has a plus max and a minus max. So that's a thing pretty funny to see from this equation. That's why it's always important to work out your ideas and do some calculations to see what is really happening, and maybe find a solution like I just did. I found a solution how to change the angular velocity or the voltage to keep it fairly constant. And how to find the I, well, I'm going to draw it in here, is when we have a motor, it has a certain current which going to, and then we're just going to use a sense resistor, and we will feed it into a amplifier, and this will go into the microcontroller. Here's a resistor, here's a resistor, and this means that there is a voltage drop across here, voltage drop, and here we have a gain. Therefore the current is equal to this resistance times a certain gain, which is actually this output voltage and this is proportional to the current, and therefore we can see what the current is, and if we know what the current is, this also becomes known. Therefore we have everything which is known, and it's fairly simple from that point on. You just change the duty cycle, and then your angular velocity becomes fairly constant. Also considered some problems with the design, and as you can see over here is when we are jumping and we displace our leg, we will create a force parallel, or actually in line with this red line, and meaning that we have a force component in this way, we have a y component and a gravitation component, and this will create a moment or a torque that is present when it's jumping, and it's not good, and I'll show you why. As you can see over here, I've just used a simulation and programmed the simulation, and I've used 100 joules as a starting potential energy, and as you can see over here, if we can take a pen. Alright, as you can see over here, this part is when it's still accelerating, and it's very small time step. Over here it's reaching maximum kinetic energy, and then it's going up. Therefore over here it's maximum height, because kinetic energy, if I can display it over here, kinetic energy minus potential energy is 0, and if you make height you make potential energy, and here you have a kinetic energy component, and then it comes back down. It comes back down, and you get your energy back. And here you can see it's reaching the ground, and is losing all of its energy into the ground. Or in this moment, it's storing all of this energy. It's storing back into the spring, and then it can go back to this part. But as I said before, this is not 100% efficient. Therefore we will end up somewhere here or even here, and therefore we use the motor to bring it back on top, so we can have our energy back. But as you can see over here is that there is a angular kinetic energy, which comes from the previous slide. If I can show it. Nope. But it comes from the previous slide where we were rotating, and we create a angular kinetic energy, which is pretty high. It's about 15 joules in this case, and it's lasting pretty long. Therefore we also have a velocity, and a velocity means we are actually rotating. And if we take a look at the next slide, what you can see over here is that the integral of this entire section of the angular velocity is equal to 13.5 radians, and 13.5 divided by 2 pi, well, you can calculate for yourself, but it's at least greater than 3 rotations. Therefore we will create 3 backflips before it lands on its face, and then we are out. But also, as you can see, that the acceleration in this uh, in this deceleration over here is really high, and if you might know, acceleration is force, therefore you will not only lose, but you will also create a problem for yourself because your robot is broken and you can't do anything. So that has to be fixed. And now for the velocities, we can see we have a component y and x, and they're currently the same because if you take 45 degrees, which was done here, which was simply 45 degrees, we get enough energy in the same direction. And as you can see over here, it's creating a nice minus g, or 9.81 meters per second squared deceleration, which is gravity. It's really linear, which is what you want. But also this over here, you see over here, this is an acceleration, and if I said acceleration means force. Therefore this acceleration in force, which can build up to 2 kilonewtons, which is a lot higher than you put into it. And again, if you don't damp it, you will break it. And this is a simulation of how it should be. Over here you can see the acceleration towards here. It makes a very significant jump because it's very little, small, meaning you just jump a little bit over and you put all your energy in the X component. Then you can see it reaches the ground and dumps all its energy again. And this was the previous. As you can see over here, here's the angular velocity, and you can see the difference, or I should call this, you can see the difference in time, because over here it's more than 1 second, here's less than 3/4 of a second. You can also see there's more energy, therefore a higher velocity, and it all makes sense actually. And now if you take a look at the angular velocity, you can see that it's almost nothing. It's not even reaching 0.1 radians per second. Therefore the integral of this part is not even 1 second. Therefore it's not even tipping a little bit. And this is how it should be. This is when you jump in a different angle and my legs are positioned backwards. When it goes directly, the component of force goes directly through the center of mass. If we take a look at the velocities, you can see a significant change. If you don't put that much energy in the y direction, you will go much faster in the x direction, almost 6.5 meters a second. And here you can see this component is A, and it's much smaller than it was before because gravity has less time to reach a high velocity. As you can see over here, it's at max. It's at max height. You can also see it in here, and it goes back down. It creates a negative velocity, therefore it goes up, and here we have a dead point, which is here, and goes back down, which is in a parabola manner. And this force is, as I said, very significantly less, and this here because here we reach ground, and this is momentum and friction, which if we take all this energy which is over here and which is also over here, if we store that again in our springs, we can jump for a very long time. So I think that was quite it. I think I was working on something else, which is kind of the dynamics, using the Lagrangian mechanics over here, using partial derivatives to determine the forces in the x and y direction. And perhaps that's for the next episode, if you like this episode. And this was basically a series to see what is behind everything that is ever produced, the engineering of pretty cool robots or anything, maybe even what you like, tanks perhaps, maybe jet fighters, rockets or anything. They all go through the phase of simply picking something and think of it, how it works, and then work it out to what it's going to do and what you expect it to do. And when it doesn't work the way you want it, you fix it until it works. So yeah, that was kind of the problem solving and critical thinking of what is behind the scenes of certain products. Some products are not even thought out and they fail. And you see why it's important to visualize every problem that might occur. And it's exactly what I'm doing with the railgun. That's why it's a little bit longer. Also, I have exams, 5 exams, coming 2 weeks. Therefore, I won't do much because I don't have free time, which is pretty sad. But perhaps after my exams, I am full back on track on the railgun. Currently, I have almost the power supply controls almost done. I only have to program it. So hopefully that's for after the exams, and then we can start building the mechanical parts of the railgun and see it fire. So I hope you enjoyed this episode of something else, and I will make more videos. I hope you liked it, to see what's happening when what people think about when they do projects like these. And I always thought it was interesting because you always see these big projects and you don't know how they work or how they were thinking when they were making it, and it's actually the most interesting part to me, and that's why I'm sharing this.